Have you ever looked up at the starry night sky and wondered what's really out there? This question has sparked curiosity in humankind since time immemorial, leading us to the fascinating world of astronomy and physics. As we delve into the cosmos, we encounter principles of physics that not only help us understand what's out there, but also reveal the inner workings of the universe. From the groundbreaking laws of Sir Isaac Newton that explain the motion of the planets, to Albert Einstein's revolutionary theory of relativity that redefined our understanding of space and time, these principles have been instrumental in shaping our perception of the universe. We'll explore concepts such as gravity, angular momentum, and the enigmatic orbits that govern celestial bodies. So fasten your seatbelts and prepare your minds as we venture into the cosmos. Let's embark on this exciting journey of unraveling the secrets of the universe. Gravity. It's what keeps us grounded, but how does it work in the vastness of space? Now, imagine you're holding an apple. It's firm, a bit cool to the touch, and heavy enough to feel its presence in your hand. Now let go. The apple falls, right? There's no surprise there. But have you ever stopped to wonder why? That's gravity in action. Sir Isaac Newton was the first to put this phenomenon into words, with his law of universal gravitation. This law states that every particle of matter in the universe attracts every other particle with a force that is directly proportional to the product of their masses and inversely proportional to the square of the distance between their centers. Sounds a bit complicated, doesn't it? Well, let's imagine that apple again. The Earth pulls the apple down, and believe it or not, the apple pulls back. It's just that Earth is so much bigger, so its pull wins out. But what if we zoom out a bit, say to the scale of the universe? That's where Albert Einstein's theory of relativity comes into play. According to Einstein, gravity isn't just a force, it's a curvature in the fabric of space-time caused by mass and energy. Picture a trampoline with a bowling ball in the middle. The ball creates a dimple, a curve in the trampoline's surface. If you were to roll a marble onto that trampoline, it would naturally roll towards the bowling ball, right? That's similar to how gravity works on a cosmic scale, with planets, stars, and galaxies following the curves created by mass and energy. So, whether it's an apple falling from a tree or a satellite orbiting the Earth, gravity is the invisible hand guiding their path. It's the reason we don't float off into space, and why the Earth orbits the Sun. So, gravity, as it turns out, is the invisible force that holds the universe together. Ever wondered why planets spin, or why skaters spin faster when they pull their arms in? This spinning frenzy is all thanks to two key principles of physics: angular momentum and moment of inertia. Let's start with angular momentum. It's a measure of an object's tendency to continue rotating. Think of it as a spinning top. Once it gets going, it wants to keep spinning. That's angular momentum at work, but there's a twist. It's not just about how fast it spins, but also how its mass is distributed. This brings us to our next concept, moment of inertia. The moment of inertia is all about distribution of mass. It's the reason why skaters spin faster when they pull their arms in. When the skater extends their arms, their body mass is spread out, increasing their moment of inertia and slowing down their spin. But when they pull their arms in close to their body, they're concentrating their mass, reducing their moment of inertia, and thereby speeding up their spin. Now let's take this concept into the cosmos. Planets, like our Earth, spin on their axes. This is due to the conservation of angular momentum. When the clouds of gas and dust that eventually formed our planet started to collapse under gravity, they began to spin. As this spinning mass contracted, much like our skater pulling in their arms, it spun faster. This is why Earth and all the planets in our solar system spin. But why don't they slow down? That's where moment of inertia comes in again. These celestial bodies have such a large moment of inertia due to their massive size and the distribution of this mass, that they maintain their spin for billions of years. So next time you see a skater spinning on ice or gaze up at the spinning planets in the night sky, remember the invisible forces at play. These principles of physics, as you see, make the universe a spinning spectacle. How do planets manage to stay in their orbits without falling into the sun? A question that has puzzled many, but the answer lies within the realm of physics and astronomy in the enigma of orbits. You see, an orbit is not just a simple circular path a planet takes around the sun. It's a delicate dance between two forces, gravity and velocity. This dance was first described in the 17th century by the astronomer Johannes Kepler, who proposed 3 laws of planetary motion. Kepler's first law states that planets move in elliptical orbits with the Sun at one of the 2 foci. This means that the path isn't a perfect circle, but more of an elongated loop. The second law, often referred to as the law of equal areas, explains that a line connecting the Sun and a planet will sweep out equal areas in equal times. This basically means that planets move faster when they're closer to the Sun and slower when they're farther away. Now, the third law is where things get really interesting. It says that the square of a planet's orbital period is proportional to the cube of its average distance from the Sun. In simpler terms, the farther away a planet is from the Sun, the longer it takes to complete one orbit. So, how does a planet stay in orbit and not get sucked into the Sun? Well, it's all about balance. Gravity pulls the planet towards the Sun, but at the same time, the planet's velocity, or its speed in a particular direction, tries to fling it out into space. These 2 forces counteract each other, creating a stable orbit. If the planet moved too slowly, it would fall into the Sun, and if it moved too quickly, it would escape the Sun's gravitational pull and fly off into space. This dance of celestial bodies, this balance between gravity and velocity, brings a whole new meaning to the phrase, hanging in the balance. Indeed, orbits, as it turns out, are a delicate balance of speed and attraction. So, with all this knowledge, what's next for us in the exploration of the cosmos? As we stand on the precipice of the unknown, the future of space exploration is a thrilling prospect. Our understanding of the universe, shaped by the principles of physics and the works of great minds like Einstein and Newton, continues to evolve, opening up new frontiers in our quest for knowledge. Imagine, if you will, the potential future discoveries that await us. Perhaps we'll finally unlock the secrets of dark matter, that mysterious substance that makes up about 85% of the universe's mass. Maybe we'll be able to confirm the existence of wormholes, those theoretical passages through space-time that could potentially allow us to travel vast distances in the blink of an eye. But even as we dream of these future revelations, we must also grapple with the unanswered questions in physics and astronomy. What is the true nature of dark energy, that elusive force accelerating the expansion of the universe? Can we reconcile quantum mechanics with general relativity to form a unified theory of everything? These are the enigmas that continue to baffle the brightest minds in the field. Yet, every question we ask, every mystery we unravel, brings us one step closer to understanding our place in the cosmos. To quote the great physicist Richard Feynman, "The more you learn, the more you realize how much you don't know." It is this humility, this recognition of our own ignorance, that fuels our journey into the vast expanse of the universe. We are explorers, adventurers, pioneers. We're driven by an insatiable curiosity, an unquenchable thirst for knowledge. And it is this curiosity, this thirst, that will guide us as we venture into the final frontier of space. So what's next for us in the exploration of the cosmos? Only time will tell. But one thing is for certain, as we continue to explore, the universe becomes less of a mystery and more of a home. So we've journeyed through the cosmos, but what have we learned? We've discovered that gravity, the force that keeps our feet firmly on the ground, is also the cosmic glue that binds galaxies together. We've delved into the principles of Newtonian mechanics, understanding that for every action, there is an equal and opposite reaction, shaping the movements of celestial bodies. Our minds have spun with the concepts of angular momentum and moment of inertia, the forces that keep planets twirling in their orbits and stars spinning on their axes. We've grappled with the concept of orbits, guided by Kepler's laws, and how these invisible paths dictate the dance of the planets around the Sun. We've ventured to the final frontier, exploring the mysteries of escape velocity, the Roche limit, and rotational stability. Through this journey, we've become more than just observers. We've become explorers, armed with the knowledge to understand the universe's secrets. And so, as we gaze up at the night sky, we are not just stargazers, but cosmic explorers, armed with the knowledge to understand a little more about the vast universe we call home.